Hello. 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 Okay. So, hello everybody. So in this video, I'm gonna give you some help in lab number 6. So let's start. Uh, swap here. Okay. So in the first part in this lab, I'm explaining to you what is don't care and how can we use it. So anyway, this is just I have already explained this very well in the lecture, and then here I'm telling you about something we call Fibonacci number. So actually, as you see here, we can create what we call Fibonacci series this way. As you see here, every number, so here I'm explaining how it works, but you can tell here every number, so Fibonacci of n, okay, is actually equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. So every Fibonacci of n is actually summation of the Fibonacci of the previous two numbers, n minus 1 and n minus 2. Okay. We are going to start with 0. So Fibonacci of 0 is 0. So Fibonacci of 0 is 0. Okay. And Fibonacci is 1, 1 is 1. So the first two are given. So Fibonacci of 0 is 0, Fibonacci of 1. I need to give you at least 2, okay? This is for 0, this is for 1, so that you can generate the rest of the series. Because every Fibonacci is actually the summation of the previous one. So now this is Fibonacci for 0, Fibonacci for 1. Here for 2. So for 2 is actually summation of the previous 2, which is actually 1, right? For 3, Fibonacci of 3 is actually the summation of previous one, which is 2. Fibonacci of 4 is actually 2 plus 1 is 3, and so on. So you can see the complete series is here. So this series, we call it Fibonacci. Anyway, so I'm not gonna as you will see later here in this lab, we are gonna design a logic circuit. The input of the logic circuit is BCD number, which is a number from 0 to 9, and the output of this one should be 0 or 1. If this number is here, if the input number here is actually one of this number here in Fibonacci, so actually the result is 1. Otherwise, the result is 0. So here, as you will see later, we need to design a logic circuit, okay, that can be used to identify or detect if the number is Fibonacci or not, okay? So here, let's start with the pre-lab. In the pre-lab, I give you here this function defined this way, and this is the don't care part. So this function has three variables, okay? And these are the location of zeros, because this is pi, and for sure the terms you don't have here, these are the location of ones. And on top of that, this is the don't care ones. Okay. So then here I'm asking you to create what? Number one, using your function here, you have to create the truth table. This is something should be easy. So given this one, please give me the truth table. Very easy. And then here I'm asking you to use the key map, and also you have to use the don't care condition to reduce it. So you need to reduce this one. You need to get the most simplified version using the don't care and the key maps. Okay. Then I ask you to draw a circuit. That's easy as well. So, and then after that, I'm asking you here to implement. Let's use this one. Implement your minimize function in digital tool. After that, here I'm asking you prepare a 3 input and 1 output circuit to recognize Fibonacci numbers from 0 to 7. Okay. Implement it using digital. Also, input should be EBC. Okay, EBC. So here I'm asking to the input has only three variables. So here I'm not asking the input to be 4. It's only yeah, because I have just said the input can be 4. For sure, it can be 4, it can be 5, it can be anything. But just to make it simple here, I'm asking you that we need to design a logic circuit. This logic circuit has 3 inputs, A, B, C. Okay, and this ABC here should give you a number from 0 until 7, and here's the output here should be 0 or 1. If here the output should be 1, okay. If the input number is actually a Fibonacci number, otherwise it's not Fibonacci number. So all what you have to do is that you have to create the truth table. So here you have A, B, C. You have to put all possible cases here, and then you have to look at this number. And then if the number here, for example, for number 0, 1, or 2, or 3, and 5, these numbers are Fibonacci numbers. So you have to put here in 0, when it is this one is 0, you have to put 1. Okay, in case of 1, you have to put 1. In case of 2, you have to put 1, because these are Fibonacci numbers. For example, in case of 8, you have to put 0, because 8 is not a Fibonacci number. By this way, you can create the truth table. We don't care here for sure, because I'm going to use all numbers here. We don't care. And then this function, I'm going to call it y. So now, because that's what I'm going to need later. So later we have two functions. We call it f. We have another function. We call it y. These are two different functions. Then you need to use key maps to simplify this one and get the circuit here. Okay, the logic circuit here. Then implement the above function using this one. You need to implement this one using digital tool. Using the data sheet of your ICs in your design, which logical path and input vector will give rise to the circuit worst propagation delay. So what you have to do here is, look here, you have, after you implement the circuit, I don't know how it looks like, but after you implement it, I want to look for the worst delay. I want to look for something like the worst delay. As I told you before, we can get the worst delay, okay? For example, this one path here. This is a short we have a critical path. This is a long path. So the delay will be controlled by this one, not this path. Okay, the longest one. Not only that, here for this one, it has 2 delays, low to high and high to low. Same thing here, low to high, high to low, low to high, high to low. Is that okay? You need to look at the worst possible case and they may not be the same. So low to high may not be the same like high to low. Okay, it may not be. So here I'm asking you to look at the truth table and look at your circuit and try to figure out where is the worst case, because it depends on the input. The delay may be different. You get what I'm saying? It depends on in the input. For example, here when this one moves low to high, it's not gonna make the same delay if it is high to low. Okay, so look at your truth table and see what's the worst combination we can get here. Worst here means the highest delay here and highest delay here and highest delay here, and thus the highest total delay. Okay. And then here I ask you to finish the breadboard circuit. This lab should be easy simply because this circuit is only these two functions are only 3 variables. Okay, so here I'm telling you something important here. For this lab, you can use as you learned in the previous labs, you can have virtual switches, not the real ones, and also you can use the DIP switches. So here, okay, or virtual switches from Discovery. Same thing for LEDs, okay? You can use virtual LEDs or you can use real ones. 7 segment, okay? You can use real ones or virtual ones. So here I'm telling you, actually, for this lab, you may choose to use the virtual ones for the switches for LED for 7 segment, the displays provided by Analog Discovery instead of using the physical ones. So it's up to you. If you want to use the physical ones, I'm totally fine. If you want to use virtual ones, also I'm totally fine. Let's start with the first one here. In the first one here, I want you to implement the circuit of F. Remember, we had two functions, F and Y, okay? And then here, I told you to use the pattern generator, logic analyzer, as I explained before. So here, you remember the pattern generator should give you all possible cases. You got what I'm saying? So here, for example, this is A, B, C. So this is C, this is B. B is actually is going to be 2 zeros, 2 ones, and so on. This one should be 4 zeros, 4 ones, ABC, ABC. Okay, A is the most significant one. Okay, anyway, so and then here displays the digit. Here also I wanna tell you who is the input digit ABC. I want to see it on the 7 segment. Actually, by doing that, you actually convert binary to decimal. Okay, so if the input is something like that, I'm sorry, something like that. So I have to see here. Oops. Okay. So because it's only 3, so 1, 2, 4. So here I can see 5 here. So it's like I just want to know what is the value of the input, binary input, but here in decimal format. I don't need to do conversion. According to the circuit developed, you need to build this circuit. Okay, the most simplified one, and you have to use 3.3 power voltage. Then along, so here if you want to use the real 7 segment, so you need to use the 7 segment and also the driver as I explained before. Again, if you want to use the virtual one, it should be okay. Again, so here we have two separate circuits. We have here, this is the input. I'm going to take the input here so that I want to see it on the 7 segment. Okay. Also, we have the output here. So you can connect here an LED as well. The reason I want to connect 7 segment and LED, just to know 7 segment is going to tell you what is the input. Okay. What is the input value here? What is the number of the input? LED should tell you if the output here is 0 or 1. Okay, in a very easy way or visual way. And then here, similar to last time, I told you make the frequency 1 hertz. 1 hertz is slow, so that actually what happens if you make it 1 hertz, the input should become 0, 0, 0 for 1 second, and then should become 1 for another second, then 2 for another second. So here it's actually you are going through the truth table. Okay. Every 1 second here. Okay, number 3 and so on. So you can see all possible cases and what are the outputs. Because 1 hertz, when you make it 1 hertz, this is the maximum frequency is going to be 1 hertz. So you can move from 1 to 1 every 1 hertz. So which 1 hertz means every 1 second. So 1 hertz means the time from here to here is actually 1 second. Okay, you can make it shorter if you want, but anyway, let's stick with what we have here. So it's going to be 1 hertz. So you can make it, then you can use a logic analyzer to see. So what you have to see here, actually, this is C and this is B. Okay, B is going to be 2 zeros, 2 ones, 2 zeros, 2 ones. Okay, and then actually I said something not accurate. So here, because this one is 1 hertz, 1 hertz is actually the time from here to here. Okay, so the time here is 1 second. That means every possible digit is going to be half a second. Okay, not 1 second, half a second. If you make this one half hertz, so by this way, so this is 1 second, 1 second. So you can change every number is you can change it every 1 second. Anyway, and then here I'm asking you to record each output and put it in a table, demonstrate it to this is very easy part. Here you are going to repeat everything again, but instead of function if, we are going to do it on function y, which Fibonacci one. It's almost, I think, everything again according to the circuit here. Okay, just very easy lab. Okay, yeah, everything is almost the same. Finally, here I'm asking you to measure the propagation delay. Okay, so based you measure the you determine in the pre-lab, determine your method and results to the instructor of asked. Okay, so here I didn't tell you for which one, so I would suggest to make it for f and y because we have 2 functions. Okay, so again, as I told you here before, the way you have to do it, the worst case propagation delay, you can see what input you can hear. You can fix the inputs, all inputs except 1. So you can put some values for all inputs except 1. Okay, so for example, put here 1, 0, is because this is the worst case. You need to find which case, what input which input out of the 8 inputs you have is going to make the worst delay. Okay, this is something you need to figure it out. Okay, so if you need to fix for sure. We have only 3 inputs, but anyway, I'm just explaining in general. We can fix two of them, and then you can come here. I can just make it change from here to it and look at the output here, what's going to happen to the output, and then you can see what is the time difference between the. We did something like that before. It should not be difficult. So here in the question here, I'm asking you the first question: why 20 cases are important? That's very easy thing to do. Verify that you developed circuit is determining the correct Fibonacci and choose the truth table to justify your answer. So here, just explain to me why you think your circuit is working. That's very simple. What is the maximum propagation delay you measured and compare it to the of the digital function if. Here asking just what is the maximum for f, and then here I'm asking does your measure here is similar to your estimation in the pre-lab or not. For sure it should be not. Okay, because what you did in the pre-lab, you just use the data sheet. Okay, in data sheets it's not gonna, they should, number one, these two numbers should not be identical, but they should be close. Okay, so because there are several reasons. I think the data sheet, here's the voltage we are using 3.3. Oh yeah, we're using 3.3. I think if you go to the data sheet, you may not find the delay for 3.3, and then you are going to get the closest one, which I think 4 volt. So this is a source of error, right? So I'm not going to use exactly the same thing. There is other things, by the way, and that's what you should understand. If temperature may have impact on chips. Okay, so but again, it's not a big impact. We are talking about very small things, but this is a source of errors. Why you are not gonna have here identical numbers? Is that okay? Another thing here, when you manufacture chips, it's impossible to create 2 chips that are very identical. It's impossible to do that. That's why there may be some variation. So that means if the digit is telling you 1 nanosecond plus or minus something, that is because it's impossible to create something that's exact for all chips. That's why already there is some margin of error here. So all of these reasons is going to make the delays here are not identical, but there should be close enough. I think this lab should be easy, and good luck.